Hi, everyone. My name is Mike Evans. I'm the Senior Conservation Data Scientist at the Center for Conservation Innovation at Defenders of Wildlife. And I'm very excited to be presenting this webinar today, sharing a little bit of the work we've been doing using satellite imagery and deep learning techniques to improve the way that conservation of imperiled species is implemented. For those that aren't familiar with Defenders of Wildlife, we are a national conservation nonprofit focused on protecting native animals and plants in North America. As part of this mission, we've worked a lot with federal agencies on their implementation of federal laws like the Endangered Species Act, but we are also increasingly interested in working with other NGO and private partners. So I'm particularly excited and grateful for the opportunity to be here at the EPRI-sponsored workshop. As I mentioned, within Defenders, I am part of the Center for Conservation Innovation, where we use science, technology, and policy to come up with innovative solutions for conservation challenges. Much of our work focuses on improving the way that the Endangered Species Act and other conservation laws and policies are implemented. And one of the ways that's increasingly become a big focus in how we're doing that is leveraging the growing abundance of satellite data to improve the monitoring and enforcement of different conservation laws, regulations, and agreements. We see the availability of publicly available satellite data as being potentially transformative to the way that biodiversity conservation is implemented because it provides this potential to get near real-time, spatially extensive monitoring of protected places and other conservation agreements. So to illustrate how we've been doing this and how we see the potential of satellite data for improving conservation, I figured we'd start with a case study. And the natural place to start is with the case of the lesser prairie chicken. So this charismatic grouse species is native to the southern Great Plains and used to be on the endangered species list until 2016. When it was removed. However, the U.S. Fish and Wildlife Service is currently considering relisting the species and is in the process of going through a species status assessment. And so as conservationists interested in achieving ideal outcomes for the species, our challenge, what I thought, was to be able to provide and integrate up-to-date comprehensive information about how the prairie chicken's habitat has changed since it was delisted in 2016, and give that to U.S. Fish and Wildlife Service. And so this is where satellite data and our deep learning techniques came in. So as you might have guessed, this is one of the first case studies that we used satellite data in to improve species protections. And we developed algorithms that automatically identified land cover change between two sets of satellite images. So in this case, a before and an after image. And that's what you're seeing here is satellite data from the Sentinel-2 satellite system within the range of the lesser prairie chicken. And our algorithms automatically identified and delineated areas that corresponded to habitat loss between 2016 and 2020. So I'll let this little demo play through and you can see what I'm talking about. On the right, we've got our 2020 imagery. On the left of the slider, our 2016 imagery. And the algorithms we developed will detect agricultural conversion, but then also other land cover change, in this case corresponding to habitat loss. And we presented these through this public app, the link is here at the bottom, specifically so users could see not only the extent of loss, but how it overlapped with different protected areas. Those are the black polygons that you're seeing. And so, as is evident from this visualization, the change detection outputs in yellow show quite a bit of habitat conversion due to oil and gas development since 2016. And so we were able to provide this information to the Fish and Wildlife Service, and they're using it in considering whether the species deserves protections under the ESA. So we were really, convinced of the power of satellite imagery and these change detection algorithms to play a role in improving the conservation outcomes for imperiled species. And the next step in our mind was to be able to basically empower the public and other conservation organizations to use these tools. Part of our mantra at CCI is we want to, whenever possible, provide free and publicly available tools and analyses to empower other conservationists. And so that's exactly what we've done. we launched earlier this year an app that is public called Habitat Patrol, and it allows a user to run our change detection algorithms on satellite imagery within an area of interest of their choosing. So we'll see here in this little demo what a user might use this app for. Upon coming to Habitat Patrol, they're going to zoom into an area west of Thunder Basin grassland and define a small AOI that they want to monitor for land cover change. The user can then select the dates that they're interested in detecting changes occurring between. Here we're going to look for changes occurring between June and August. And then they run our algorithms in the background, and the app serves up before and after satellite imagery based on the times they defined, as well as highlighted areas that the algorithm detected as change. So here we'll see the before image. After image, we see there's some land clearing. And then in purple, when we turn on the change layer, the user is presented with the automatically identified changes. So we're really happy with the performance of this algorithm, and we think this tool could be used as is by any number of organizations and groups to monitor different protected areas that they're interested in, really democratize this process. As you can see, there are some limitations to the outputs of these change detection algorithms, and that's because everything we've done so far has been pixel-based. And so we can sometimes miss precisely identifying the extent and boundaries of anthropogenic features that show up on the landscape. And so what we are really interested in doing, and what we've started to put our efforts towards, is generating the next set of deep learning algorithms to detect change. And these are based on computer vision models. The reason that we are excited about this, and we think this stands to advance our conservation work using satellite images, is computer vision models basically take advantage of the spatial context. So the shape and surrounding area, in addition to the per pixel reflectance values, to identify unique objects that we teach it to find on the landscape. And so again, to note, we're using all free tools to do this. We've been accessing satellite images through Google Earth Engine and implementing different versions of UNet models, for those that are familiar, in TensorFlow using Google's cloud platform computing capabilities. And so the first class of objects that we sought to detect using computer vision was actually all the solar arrays, ground-mounted solar arrays in North Carolina. This is a project that the Nature Conservancy asked us for help with because they needed to have an updated map of these things for an analysis they were doing. And so what you're seeing here is a publicly available app that shows the outputs of our computer vision model detecting solar arrays. It highlights them in orange here, and you can see the underlying satellite imagery. And the model is basically identifying and able to delineate those objects in the satellite image. So this is really cool and encouraging, and we are interested in continuing to train models like this to find other features on the landscape. We also think, as I mentioned before, that it could represent a substantial improvement to our change detection methods. So we've begun developing computer vision models using a UNet architecture that do just that identify specifically anthropogenic habitat loss on the landscape. So we'll watch one example of this in a forested area play through on the left. We've got before and after imagery, some land cover clearing, and also some other phenological changes that we really don't want to be detected. And so the UNet model highlights just those sort of new anthropogenic land cover clearings in purple, able to take into account the shape and context there. Another example from a different environment, we've got before and after imagery showing some oil and gas buildout down in New Mexico. And here's the outputs from our computer vision model identifying those anthropogenic land use changes. So we're really excited and encouraged by these early results from this new approach, and are looking to continue to build and improve upon these models. So yeah, our next steps for all this work having to do with computer vision and satellite imagery is we're first going to expand our solar analysis. We are running that model back through time in North Carolina so that we can, in a conjunction with collaborators at George Washington University, we're interested in being able to model and predict what factors guide the development of solar energy in the state. We're also constantly releasing new features in Habitat Patrol, the app that I had been showing before. And the next one to come out is going to be an ability to use the Fish and Wildlife Service database called ECOS to automatically pull in the ranges of species on the endangered species list. So for instance, here a user can type in a species name, and we'll hit the ECOS API and pull that information into Habitat Patrol so user doesn't have to draw these areas or upload them themselves. The next step, of course, then, is to upgrade our change detection algorithms to use the UNet computer vision models that we've been developing. And so the long-term vision here for Habitat Patrol is to have both the ability to automatically ingest areas that are important to monitor, species ranges, but also potentially other protected areas, and use this new efficient and really precise class of deep learning-based computer vision models to be able to monitor those areas efficiently, frequently, and pretty effectively. So I really appreciate y'all tuning in, taking a listen. If you have any questions about what I've shared here, want to get in touch about the work we're doing with computer vision and satellite imagery in the context of conservation, please feel free to reach out to either myself or CCI's director, Jacob Malcom. And I would also encourage you to explore the many other conservation tools that we have at our website down at the bottom there.